Buenos días. Okay, let me introduce myself and Netflix with a quick story. Hello? Okay. 2007, Netflix made a huge gamble. They went from a DVD company to a streaming online video content company. The image you see here, first online advertising. And the first device that supported this same year, I also made a huge bet. I decided to move from Colombia to the US to join the University of Georgia as a software deal for me. I left family and okay. Bueno, cosas pasan. 2011, Netflix expanded globally, and it was launched in Colombia. It was big. All this great content was now going to be available to the rest of the world. And not only that, Netflix started investing in local content. So now our Colombian content was going to be available in one place for the rest of the world. Same year, I was expanding my knowledge in computer science. I was doing my master's degree at the University of Georgia with focus on distributed systems, networking, and security. Fast forward to 2017, Netflix reached a huge milestone, 100 million subscribers globally. This same year, I also reached a big goal for me. I joined Netflix. So Netflix and Netflix Open Source Technologies has shaped me as an engineer in distributed systems. I was a big user of Zool, Hystrix, and other open source technologies to implement microservices at scale. I joined the Edge engineering team. The Edge team manages the most critical services at Netflix. So I was very excited to join this team. In 2018, unfortunately, this happened. Thousands of customers around the globe experienced an outage. The outage was big enough to make Twitter. People were freaking out, couldn't watch their favorite shows. And unfortunately, it was me who caused this outage. This is why I'm here today to take you to a journey behind the scenes on how to run critical services en Netflix. Mi nombre es Manuel Correa. Soy Senior Software Engineer en Netflix. Yo estoy muy contento de estar aquí en Colombia mostrando mi trabajo en Netflix y espero que les sirva lo que es la presentación. El día de hoy la presentación la voy a dar en inglés. Okay, think about this. You open Netflix, you pick your favorite show, La Casa de Papel, and you hit play. Seconds after that, you're streaming your favorite show. However, have you ever wondered what happens when you hit play? What are the critical services and everything that happens between play and the video to start streaming? Well, let me give you a quick overview. When you hit play, the first thing that happens is the device requests a manifest in our AWS infrastructure. This manifest is a document that contains information about the playback session. Things like audio, language, and the location of the video. So the next step for the device is to fetch the content. This content is usually stored in the closest ISP. The content, however, is stored encrypted, and it travels to the network in an encrypted way. So then the device has one last step, and it's to request a license. A license is essentially a key that can decrypt the content. And at that time, the device is ready to stream the content. So all these three steps happens between that time. They're critical steps. Today, I'm going to focus on the Playback licensing service, which is the service that I'm responsible for. The license service is a very complex service. It's composed of 18 microservices and 2 data stores. We're responsible for the license workflow, applying the content policies, downloads, and device retirement. All of that with just one goal, a very high available and reliable system. So coming back to the outage. So one of the things that I really enjoy from Netflix is that we embrace failure. So even though I was the one who pushed the button, I had a lot of groups in my team and many other engineers work with me to find the root cause. And not only the root cause, to find a way to learn from this incident. We wanted to be able to find the gaps, investigate, and share this with the rest of the engineering team. So for this, we focus on 3 questions. What was the level of fault isolation on this outage? Why wasn't this code or this bug caught in our testing and deployment pipelines? Finally, how can we prevent this in the future? So today, I'm going to focus on these 3 topics. I'm going to also show you a little bit of a sneak peek on how we think and implement this on Netflix. So we're going to talk about fault isolation first, deployment and testing, and service-to-service communication. Let's start with fault isolation. In a distributed system, fault isolation is defined as any failure in a subsystem, its consequences, or the blast radius is minimized to only a subset of customers or users. And you want to optimize for that. There is a lot of ways to implement fault isolation. And today, I'm going to focus in 3 basic techniques on traffic management. So our critical services are deployed in 3 AWS regions. That means that all our global traffic is divided in each of these 3 regions. And we have an active and active architecture. That means that a request in US East can be also answered in US West 2. What this allows us to do is, if one of the regions is having issue, let's say US West 2, we're able to migrate all traffic to the other 2 regions without customers feeling any pain. We exercise this experiment like every week. This allows us to isolate failures from AWS or perhaps self-inflicted issues at deployment time. The next 2 techniques are what we call traffic sharding. Sharding is usually a term defined in databases. So a shard in a database is a logical or physical partition where using different criteria, you can divide your data so that you can accomplish perhaps something, a high available system or more consistent or so on. If you apply the same concept but you apply it to traffic, you can think about the criteria where you can divide your traffic to accomplish fault isolation. So we have 2 implementations of this. Traffic sharding by functionality and traffic sharding by criticality. Fault isolation through functional sharding is essentially dividing your microservices for a specific use case, for a customer use case. So in this case, for the license service, we will have a microservice to serve only mobile devices, a license service for browsers, and a license service for TV. All of this in a common framework that we can control. They will all have the same API surface. And using our API router, we're able to write the device to the right functional chart. So it's the same application, but dividing the traffic in multiple functional charts. The next technique that we use is critical versus non-critical traffic. So critical traffic is an API that is essential for the play experience. That means if this API is down, well, customers like you won't be able to play. Because of that, we have very high service levels agreements. And we have higher performance considerations for this type of traffic. In the other side, for non-critical, these are APIs that have a very well-defined fallback. So if the API is having issues, you as a customer will experience some service degradation as opposed to service loss. we're able to have some flexible SLAs. And this type of traffic or clusters allow us to experiment. We can do stress testing, tuning, and so on. This is essential. So at this point, this sounds like common sense. You may be wondering, well, how do you implement that? So at Netflix, we're a big user of Spinnaker. Spinnaker is an open source multi-cloud continuous delivery platform. It allows you to control your clusters, testing, and deployment pipelines. Think about the Spinnaker like a one level of abstraction of your cloud infrastructure. In this case, AWS for us. With Spinnaker, this is a typical view of a service. In here, the green boxes are EC2 instances or containers, and the white box around it is an auto-scaling group. In one view, we can see the regions that we're deployed to, as well as the cluster sets based on criticality. So when you see this as a service owner, you're able to very quickly understand the topology of your service. By applying these techniques, we have achieved a very high level of fault isolation. And for us to have an 100% outage is really, well, sometimes or minimized for just a subset of customers. But we did have this issue this day. And in this case, even though the outage was big enough to make social networks, the outage was concentrated in just one device type. So that worked really well for functional sharding. However, the outage was felt globally on that device type. What we didn't have was, at that time, deployment windows. So we worked with the Spinnaker team to implement deployment windows. So now we're able to deploy in each of the regions in a different window without overlapping. Also, taking into consideration the spikes and the customer behavior in each of the regions. So this was great. As I mentioned, Spinnaker not only allows you to control your clusters, but also your deployment pipelines. On the outage, one of the questions was, well, why wasn't this code change caught in our testing and deployment pipeline? So before I can answer that, let me give you a quick sneak peek on how we think about testing and continuous delivery. In my team, continuous delivery, by the way, continuous delivery is usually a term that is overused in the industry, and there's a lot of definitions out there. So for us, this is what we mean with continuous delivery. Services and critical services are deployed daily and on demand. Very likely, yesterday, when you were watching Netflix, we were deploying our services at the same time. The master branch exercises the deployment and testing pipeline every morning, automatically. Think about that. 18 microservices all at the same time, exercising the testing and deployment pipeline. Finally, our microservices, as well as yours, have probably thousands of dependencies. Well, we decided that for us to control our dependencies, we like to ping it the latest release. So we never ping to a specific version. What that means is every day we're picking up new dependencies and exercising the testing pipeline with those dependencies. And you might be thinking, well, this is a critical service. Why would you ever do something like this? And for us, the answer is simple. We have embraced testing in production and continuous delivery because that's the only way that we have to really understand the state and to predict the system in a specific environment. The view that you see here is a Spinnaker pipeline for a normal deployment in one of our services. We want to optimize to deploy fast, but safe. So on the safe side, we have many stages on testing. The first one is what we call a canary. A canary is a technique that we use to compare a new build with the current build that is in production. So we spin up a new cluster with this new build. We spin up a cluster with the current build in production, and we compare metrics like CPU, latency, threads, and so on. All that information is captured. And you can see things like, well, the correlation between the metrics is really close. So this is kind of expected behavior. But in other cases, you can see the same metric for the new build and the current build being a little deviated. And that doesn't mean that it's bad, but it does raise some concerns. So we have an open source tool called Cayenta that aggregates all this information and come out with a score. Then we can use this score and a threshold to stop the deployment or to continue the deployment. If it's a bad score like this one, we will have a human being trying to understand what happened with this specific build. So this allows us to compare the new build that is about to be deployed in production. What about, to answer the question, how healthy is my service based on the well-known test? So we have this concept called service diagnosis. Each of our microservices have an endpoint that by calling it, it will respond with a metadata set about how healthy is that specific service on that environment. So in this case, it will answer back with, yes, I can generate a license. I can generate a license with restrictions. I'm able to connect to the database, CAD, and so on. We then can capture all this information, in this case in a container, and assess the health of the system. Think about this like an integration test, but in production. So service diagnosis gives the signal for the server-side deployment. What about the client side? At the same time that we're doing a Canary, we apply an end-to-end test. An end-to-end test is a Netflix control app that is deployed, and the traffic for that specific microservice is related to the new build. Then we're able to run functional tests on this application. Functional tests are very basic tests, like can the application still play? Can you still play multiple titles? Can you still pause? And so on. So we don't want to break that functionality, that basic functionality with a new build. This is key. It gives us a signal from the client side in the server-side deployment. Canaries, service diagnosis, and end-to-end testing, they all test the knowns. What about the unknowns? As part of this, we also run chaos experiments. Chaos experiments are basically injecting failures into the new build to see if it's still resilient enough. For that, we use some open source tools like Chaos Monkey and Chop to inject failures in our dependencies. In that way, we're able to know if the new build is still resilient and if there is any unexpected changes. With all this information, we're now ready to deploy to our non-critical cluster. We deploy to the Hello? Okay. We deploy to the non-critical clusters, and then, at a period of time, we're able to gather some metric and fully deploy to critical clusters. Happens for a single deployment. Sorry. So all these steps. Okay. So all these steps are vital for us to understand and predict the state of the system. And I will encourage you to invest time in your deployment pipelines. However, in this case, with all of that, we couldn't cut this issue. And it happens to be that this code change, it wasn't a code change. It was a configuration change. And at the time, configuration used to travel to a different place. We were able to change it dynamically and with no testing. and globally. So that wasn't good. After many talks with my team, we decided that configuration should be treated as code, as well as performing testing on configuration. This configuration change was the configuration change that affected the load balancer between the client and the server in the microservice. This is why I wanted to show you the last topic, service-to-service communication. At Netflix, the service owner is also responsible for the client library that is calling that service. What that means is every time that we deploy a new service, we also release a client library for our callers to consume. This library can be in Java, if the caller is in Java, or Node.js, and so on. But the responsible party for the health of that library is the service owner. Historically, we have used frameworks like Hystrix for circuit breaking and bulk heading, and Netflix Ribbon for load balancing. They're still deployed today in production. However, newer services are now using gRPC. gRPC was open sourced by Google in 2015. Google, Netflix, and other companies has rallied around this framework to implement the best practices around RPC communication. For us, it really fits our SLAs. It uses protocol buffers, it auto-generates the client, it is polyglot, and it was designed with performance in mind. I know this is a lot. Just want a quick introduction of what gRPC is. gRPC uses protocol buffers. And protocol buffer is an agnostic declarative language to create data structures. So in this case, we have protocol buffers to define a movie with an ID, title, duration, and so on. Then we can compile that into a Java module class. And you can utilize it like this. And perhaps you can serialize that object into a file. Then, in Node.js, you can load that file and still have your object. This is very powerful. You can communicate two different languages and many, many more through one definition of your data structure. gRPC allows you to define your service in protocol buffers. And that is really powerful. The service now can be abstract away from the language, and you can create your service and client stubs in a specific language. By doing that, you also standardizing in the way that a microservice communicates to each other. So gRPC offers client streaming RPC, server streaming, or bidirectional channels. Finally, like I said, gRPC was designed with performance in mind. It runs over HTTP2. It gives you error handling. It also allows you for extensions. So concurrency limit is an open source project from Netflix to, It gives you load balancing, interceptors, and security through TLS. So all this concerns in just one framework so that the developers can focus on the business logic. However, for us, it's vital to understand the RPC framework that you're choosing, regardless of what it is, if it's REST, gRPC, or if you still use SOAP. It's very important to understand the consequences of a configuration change, as well as the underlying technologies used for communication. I believe that communication in a microservice architecture is probably the most important piece of the architecture. So coming back to the outage, like I mentioned before, the configuration change affected the client and server communication. And in this case, we really didn't understand the implications of that configuration change. We didn't have enough information at development time to reason about this change. Now, what we decided to do is introduce client and server configuration integration tests. This allows to always have a synchronized configuration between those two. So today, I talk about fault isolation and how to implement it, deployment and testing, and service-to-service communication. For fault isolation, by following very simple and common sense techniques, you can achieve very high level of fault isolation and minimize the blast radius when you have problems. By continuous testing and continuous deployment, you can understand your system. That's the only way you have to really understand the behavior of your production system. Finally, choosing the right RPC framework is very highly important for a microservice architecture. And I encourage you to study and spend time picking the right framework for your use case. Finally, any gaps on these issues, on these basic concerns, are the usual suspects in an outage. And for me, on my first years on Netflix, it was a lesson learned. And not only that, putting the technical part aside, embracing failure and understanding that the only way to learn is through failure. And through this outage, we learned a lot. We were able to identify gaps, and now, hopefully, we're able to support you as a customer in a better way. And with that, muchas gracias por su atención.